make sure your microphones are muted. And when I give you guys a chance, please ask questions. And let me share my screen. Okay. It's 3 o'clock, so we're going to start the next uh, session of the practice problems, where I focus on the energy and light and the quantum numbers of the orbitals and the electron configuration. Right. So the first question asks about the energy, some questions based on the energy and light. And the first question, what is the frequency of light with a wavelength of 105 micrometers? Right. In this case, mm, right. Here it says the light. So the equation that we must use is the C equals lambda and nip. C is the light speed of the light, and the lambda is the wavelength of the light, and nip is the frequency of the light. So we here we should solve for the frequency of the light. So I'm going to rearrange this equation as nu equals to C over the lambda. Right. So we are given the wavelength. But what is the speed of light? Yes, the speed of light is a constant that will be given. So you can use that 2.99, whatever the constant that will be given. You should use that with the exam. 2.99 that multiplied by 10 to the 8 meters per second divided by the lambda. Right, now look at this. Speed of light is given in meters per second, but the wavelength is given in micrometers. So please make sure that you will change this, the 105 micrometers into the meters. So we must get the relationship. Okay, so the 1 meter equals 1 times 10 to the 6th micrometers. So in that case, you can get solve for this, the frequency of light as 2.86 times 10 to the 12th per second. Right. That is the frequency of the light. Okay. Next, what is the wavelength of the light in meters with frequency? Right. Now the frequency is given in hertz. 1 hertz equals 1 per second. Right. So you can simply get that as in per second. Right. So the wavelength. So again, we rearrange that equation to solve for the wavelength. Wavelength will be equal to the speed divided by the frequency. Again, we'll use the same, the speed of the light, 2.99 times 10 to the 8 meters per second divided by the 1.88 times 10 to the 5th per second. So I'm gonna post the answer key for this practice questions as well, so you can go over that as well. So I will just leave it there, right, in order to save the time of this session, right. The next one, what is the energy of single photon? The first two equations were just used only that equation. Now we are talking about the energy as well, right. So with the wavelength of the let me take another color, right, 505 picometers, right. So now we are going to use this equation as well. E equals h nu. The h is the Planck's constant. The value will be given with the test. So all these equations will be given as a separate, the printed sheet. The periodic table will be given as a separate printed sheet, and you will be also given some blank paper for your scratch work. So you all need to bring a pen or pencil and your calculator for the exam. Right. So the we will solve for the nave. We should find the value for the frequency because the value of the h will be given. So the frequency will be equal to the speed divided by the wavelength. So that will be equal to 2.99 times 10 to the 8 meters per second divided by the lambda. Now the lambda, the wavelength is given in picometers. Again, we must convert the picometers to meters. So mm, will be oh, will be equal to like 1 meter equals to 1 time 10 to the 12th picometers. So picometers to picometers will cancel out and we'll get the meters. And here you will see the meters to meters will also cancel out and you will get the answer in per second. That those are the units for frequency. So the answer will be 1.93648. Oh, sorry, just 13468 per second. Then you will use that in the E equals h nav equation. You will use the Planck's constant, that which is 8 6.6 to 607 times 10 to the negative 34 joules per second multiplied by that the frequency we have obtained from that the equation above, and you can solve for the energy, right. Do you have any questions? Okay. Since I do not get any questions, I will move forward to the next question. Now we will talk about the different um, orbitals. Now you are given like the different shapes of the orbitals, and you are asked to find the to identify these. This is an S orbital. S is like a globe. The shape is a globe, and that's the S. And this is the P orbital, dumbbell shape. That's the P orbital. And these are the D orbital, the shape. So here, when you have drawn it to against the z-axis, you can draw it like this. But if you draw it the other way, then you will draw this the white over orbitals over here, and this is again another way how we can um, uh, demonstrate the shape of the d orbital. And here is the p orbitals, which has 6 orbitals. Okay, suborbitals. S has 1 orbital, p has 2 orbitals, px and py. D has, like, S has just one, p has the p oh different, oh sorry, I made a mistake. There are px, py, and pz, and d has dx, dxy, dyz, like that, 5 different orbitals. F has 7 different types of orbitals. Right, those are the shapes. You have any questions? Next, we are now trying to write the electron configuration. When you are trying to write the electron configuration, you should follow 3 different principles: Aufbau principle, and Hund's rule, and the Pauli's exclusion principle. Aufbau principle will tell you that you should fill the electrons first to the lowest energy. Right. And the Hund's rule said, if you have any 2 suborbitals at the same inner level, you should fill it one on each at the equal level. And the Pauli exclusion principle will tell you, if you're going to fill 2 electrons onto one orbital, then the spins of these electrons should be opposite. Those are the rules that you should follow. Right. The boron. First of all, we must know the number of electrons in the boron. Boron has 5 electrons. Right. So we have the 1s. How many electrons that we can fill into 1s? The maximum 1s2. Right. So the energy level 1 has only the s orbital. So that was filled. Next, we'll go to the second energy level. In the second energy level, we have 2 types of orbitals, 2s and 2p. Right. Again, any s orbital can have maximum the 2 electrons. Right. So now we have filled 4 electrons. 2 plus 2 equals 4. How many electrons left? Just one. That remaining electron will go to the p orbital. So the electron configuration for boron is 1s2, 2s2, and 2p2. Questions? Right. Next, we'll go to the sodium. So we will get the electron, oh, and the Nobel gas electron configuration. The Nobel gas electron configuration is, we take this one inside, and the Nobel gas. What is the Nobel gas? Which has 1s2 electron configuration? That is the helium. So we'll put it inside there, and we'll write this 2s2, 2p1. So whatever the one outside or beyond this, the Nobel gas configuration is the valence electron configuration. This is the valence shell, or the outermost shell. Valence shell. Right. Next, we will move to the Next question, sodium. So what is the atomic number for sodium? The atomic number for sodium is 11. So that means a neutral atom of sodium has 11 electrons. So let's fill those electrons. 1s2. Next, that is filled. We'll move to the second energy level, 2s and 2p. Right. The maximum that can go to the s, again 2, and the maximum can go to the p orbitals are 6 electrons. 2 plus 2, 4, and here is 6. Right. 4 plus 6 equals 10. And how many left? Just one electron. So the second energy level has only the S and P, and we have to move to the third energy level. We have remaining just one electron that will be filled to the S orbital. Right. Now, what is the uh, um, noble gas that has these things? Okay, the 3s1 is the outermost shell, or the most outside the energy level, whatever the uh, uh, embedded inside the atom is the noble gas configuration. So that noble gas for that configuration, 1s2, 2s2, 2p6, is the neon, and we'll put neon inside, and the outside we'll write 3s1. So 3s1 is the valence electron configuration for sodium. Next, we'll move to the iron, and the electron configuration for iron is 26. Right. Okay, let's work on that. 1s2, 2s2, 2p6, right? 10 electrons were filled, but 16 left. So then we'll move to the third orbital. It has 3s, 3p, and 3d. Okay, right. 3s can take the maximum, the 2 electrons. Then let's count. 10 plus 2, 12. Maximum again for all p orbitals, 6. Then 12 plus 6, 18. And now we have a problem. In energy levels, according to the Aufbau rule, the before it fills the electrons into the 3D, the electrons will move to the 4D. Okay. So the 4D will be filled, sorry, 4S, 4 electrons will be filled to the 4s. Then 4s can take 2, and we have remaining how many? 20. Oh, now we have 20 electrons were filled. So we have 6 left, and all d orbitals. D orbitals, like there are 5 different d orbitals. One orbital can have 2 electrons. So the maximum is 10. So d electrons can take that, the remaining 6 electrons. So this was said, okay, right, according to the no Aufbau rules. So then you can simply change it. Let me see. I'll write 4s2 first and 3d6. Okay. So the 4s2 3d6 is the valence shell. This is the valence shell, and whatever inside is the electron configuration for the argon, and here we can write 4s2 3d6. Right. Okay, so like that, please try to okay, let me see. We can fill these, we can write these the electron configurations. Okay. You have any questions?
Will we need
Yeah.
to just remember the chart?
Yes, you should remember the chart because the first energy level, the second energy level, like that. The first energy level must have the 1s, the second 2s2p, third 3s3p3d, 4s has like the four different things like that. Yeah.
Will we have to know the more complicated charges for ions? Like, because I know some of the elements on the periodic table, like the transition metals, they vary with their charges. Are we going to have to remember those? Or are we just going to have to know the basic ones, like, you know, period one is a positive one, period two, positive two, and then, you know, going over to period 13 is positive three, and then period 14 is sometimes positive 14. Sorry, period 14 is positive four, minus four, and then so on.
Right now, no. For this,
Okay.
up to the first unit exam, no. But beyond that, you will learn how to make those ions.
Okay.
When you were taught how to make those ions, then you don't need to worry about memorizing these things. As an example, look at these the valence shell electron configurations. That's why this question asks you to or give it a hint. Write the noble gas configuration. Then you'll play with only the valence shell electron configuration. Always it is tend to have the more stable electron configuration. The formation of ions, the what is the objective of formation of an ion? The formation of an ion is to achieve the most stable noble gas configuration. So in that case, they'll choose the easier way to do that. As in group 1, so here the sodium is an example of an element which is in group 1. So its valence electron configuration is, look, the S1. Here the S1. So what is the easiest way to get the another, like the, because 3s has or 3p 3d, getting all other like 19 electrons filled, or releasing just one electron? Yes, the easier way to release that the single electron out and making the plus one charge ions, so that the group 1, remember that group 1 always make plus 1 charges. Group 2 makes plus 2. Group 3 plus 3. Group 4, carbon. The first one is the carbon. Carbon is bit tricky. Sometimes it makes the plus 4, sometimes it makes the minus 4. But whatever in the bottom rows will always make the plus 4. But when you go towards the right side of the periodic table, except the group 18 or the 8, the noble gases will, they are inert because they have the valence shell electron configuration. But if you talk about, if you take an example, oxygen will have the electron configuration as the uh, 2s2 2p5. So in order to achieve a noble gas configuration, it it needs only one more electron. That would be easier, rather than losing 7 electrons. So it will choose that way to take a one more electron and make it into 2s2 2p6. So it is taking electron in, so making a negative one charge, like that. So you don't, the transition metal ions, that's why they were called as transition metal ions, because some metal ions will make more than one charge of ions. So you don't need to worry about those things that much, because we are not writing the names yet. When we go to that, the physical properties of elements, where we will talk about those ions in details. Right. Okay, I hope we have covered that. And next, I will go to the question number, the B of the question number 3, part B. The electron configuration of the following elements are exceptions to the Aufbau rule. Write their anomalous noble gas configurations. Right. Chromium, copper, molybdenum, silver, palladium. They are all in that the transitions or the D block elements. Right. In this case, why it is not following the Aufbau rule? The Aufbau rule means, okay, this is 1s. Okay, uh, okay, oh, energy level 1. This is the energy level 2. This is the energy level 3, and like that, energy level 4. So according to the Aufbau rule, all the electrons should be filled to the energy level 1, the orbitals in the energy level, next the energy level 2, the energy level 3. But the problem is, when the electrons, before electrons are filling to 3D, they will be filled into the 4s. The reason is, when we considering those energies of the orbitals, this is 1s, this is 1s, and this is sorry, 2s and 2p, and here is the 3s, 3p, and then we'll have the 4s. After 4s, we'll get the 3d. Right. So here you will see the energy of the 4s orbital is lower than the 3d. That's why electrons will fill into 4s orbital before they will be filling into 3d. That is the reason. Okay. And then next, the when we talk about the 3D, they have semi-permanent rules, right? Always, okay, there are 5D orbitals, right? So when there are, here is the 4s and this is 3D. When the 3D has 3D4 electrons and 4s2 electrons, what happened is, the one electron from the 4s will move to the 3D and will arrange this into the 3D5 and 4s1. This 3D5 4s1 is more stable than 3D4 and 4s2. Again, when there is a 3D9 and 4s2, again the same thing will happen. We'll take a one electron from the 4s2 and this will be rearranged to a 3d10 and 4s1. Okay, because the 3d5 and 3d10 are more stable than having the 4s2 and other, like the half, like 3d4 and 3d9 configurations. That is the reason. So when I talk about the chromium, when you write the noble gas configuration, you will get the argon 4s2 3d4. But this is 3d4. So this is, but it can rearrange to it's the half filled stable configuration. So that will be rearranged to a 4s1 3d5. Right. Again, with the copper, it will have the noble gas configuration as argon 4s2 3d9, that will also rearrange 3d9. So it will take just one electron from the 4s and arrange into the very stable 3d10 configuration. Right. Again, with the molybdenum, we'll have the krypton and 5s1 and 4d5, 4d4. So that will be rearranged to a krypton, sorry, 5s2. Okay. It will be rearranged to a 5s1 and 4d5 like that. So these will rearrange to these d5 or d10 configurations, taking an electron from the next s orbital. Questions? Okay, right. If you don't have any more questions, I will move to the next one. Right. Here, this is a very good question where that you are given the energy level diagram and you will see some electrons were filled in. So for the ground state, it says it is ground state, so that's a neutral atom. And you'll have set of questions about below that the energy diagram, that you will use the information given with the energy level diagram to answer these questions. Right. The first question, identify which element corresponds to the electron configuration.
I actually do have one question. I'm sorry.
Uh,
Um,
from the previous one?
yes, and it kind of ties into this one. So when it comes to the transition metals, it only takes that one electron when the question pertains to a transition metal, if I'm
No,
understanding that.
no. It will take only to rearrange to the D5 or D10.
Okay, so if it goes to D5 or D10,
Yeah. Other than
okay,
that, like when you have that like the D7, no, then no change will happen there.
okay, okay. Thank you.
Yeah, you're welcome. Right. If I come to this question back, um, the how we can figure out the element which belongs to, or which owns this electron configuration. So what the simply you just count the number of electrons. So this is a ground state one, so the number of electrons will equal to the number of protons or to the atomic number. So you will count the number of electrons and you will get the atomic number. Okay, so this one, okay, when you count this, the number of electrons, you will get it as the 28. So the atomic number 28 belongs to the nickel. Right, nickel. Oh, if I write the name, okay, that's the one. Right. What is the electron configuration? So that is very like a straightforward question. You can just write those things. Okay. Since I'm going to write that, mm, I'll write that the equation, the electron configuration here. You can just see how I am writing this. I'm starting with the 1s2 and then go to the 2s2. Then you will see all 6 electrons are filled in p orbitals in energy level 2, 2p6. Then we go to the 3s2. Then you will see all 6 electrons are filled into the 3p's, 3p6. And then you will see this, the 4s2. And how many electrons are on d orbitals? 3d. There are 8. Okay. So that is the electron configuration for this element. Right. We'll go to the next one. What are the principal quantum numbers for the uh, s- uh, um, for the circled electrons? Right. Let me just describe something. What quantum number? Quantum numbers are used to give the exact location of the electron. You have already talked about the uncertainty principle. We cannot exactly tell somebody like where the electron is exactly located inside an atom. But as an example, we found a method to we are trying as much as possible to give the location for this electron, right? So as an example, if somebody asks you as an example, if you are trying to find my office in Wake Tech, so then I'll tell you I work at Wake Tech Community College, right? That's the energy level, Wake Tech Community College. But there are different campuses in Wake Tech. Wake Tech. Wake Tech has different locations. Then I'll say it is the North Campus. Okay, now why? Like I'm make smaller the area, right? I'm trying to they limit the search area. Then, but still in North Campus there are different buildings. Then I say, okay, the building B. Okay, now you have only one building to look for. It's building B. Then in building B, you will wonder, okay, there are 4 different floors in building B. In which floor do I have my office number? Then I'll say it is in the the uh, 4th floor. Okay, you'll come to the 4th floor. But again, in the 4th floor, there are different rooms, lots of rooms. So then I exactly say, okay, my office room is 444. Okay, like that. I am just um, making the boundaries. Okay, I am giving you certain directions to find my office exactly. That's why. That's the same why we are using these the quantum numbers to definitely to try to locate the electron, right? I just wanted to give you a basic introduction on why we use these quantum numbers, right? There are 4 different quantum numbers: n, l, ml, right, and ms. N is the principal quantum number, L is the angular quantum number, ML is the magnetic angular quantum number, and the MS is the spin quantum number. Right. N is actually the energy level. So here, now the first one is this, right? This one. Okay. What is the energy level for that electron? N. N is equal. mm, N is equal the 2. You all see that because it's in the energy level number 2. L. L can be from the ml, like the what is the like the you can right, the energy level L is the orbital, the shape of the orbital. In energy level number 2, we have s orbitals and p orbitals. Now you need to give the which orbital is that. You will see the p orbital. When I give the numbers for the L, S has 0, P has 1, D has 2, like that. So this is in the p orbital. So L will be equal to 1. And ml actually we can have different values. It goes from negative L to positive L. What is that? P orbital has three things, right? So px, py, and pz. So that there are three orbitals. That means -1, 0, and +1. So this is in the first one, right? So this is my sometimes my pen start -1, 0, and +1. Right. Where is that electron in? It's in the -1. Why? Right. -1. Now look at the next, the spin quantum number. It's easy. The spin quantum number can have only two values. If it is up, ah, what's going on? If it is, it has only two spin quantum numbers, plus half or negative half. Plus half is the upward one. The downward electron will have the minus half. So when you go there, it was the downward one. So then the ms will be uh, the negative plus half. Right. Questions? Yeah.
So are we using for the ML, the reason why that's -1 is because it also is pointing down.
Pointing down will be used for the spin quantum number. Okay. The negative one is the px orbital. Okay. Let me go to the next example as well. Then you will understand. Right. The next one is in here, the 4s1. Okay. Here. I will use a different color and I'll use it over here to explain it. Right here. Now, the principal quantum number first, right? The principal quantum number or the energy level, N equals, which energy level is that? 4s is in number 4, right? Next, the energy level 4 has 4 different types of orbitals. Okay, 4s, 4p, 4d, and 4f. Again, s, the angular, quantum number is 0, p. The value for the L is 1, d 2, f 3. So this is in s. So the L should be equal to 0 because the electron is in s orbital. Next, when it is in 0, again, so the ml, what is ml? Ml goes from negative L to the positive L. Since it is 0, it has only one value. So the ml will be 0 again because it has only one type of sub orbital. That's the reason. Now, look at the orientation of the electron. It is pointing down. So as I have told you there, when it is pointing down, that will be negative half. So the ms will be equal to the negative half. Right. Okay. Um, the next one, okay.
And that
I will,
question was only pertaining to the circled regions, right?
yes, what
When it came to identifying the four quantum numbers.
mm-hmm.
Okay.
Yeah. Here we are trying to figure out the all four quantum numbers for those the highlighted or the circled electrons. Right. So I will erase this portion just to go over the next one. Right. Um, right. Now we'll look for this one. Right. Uh, Again, principal quantum number. Oh, in which energy level is that? The n equals, it is in the 3D, so n equals 3, third energy level. Next, we'll look at the L. In which orbitals are those? In d orbitals. For d orbitals, okay, here s equals 0, p equals 1, d equals 2, f equals 3. So now you will see, since that electron is in d orbitals, the L value should be equal to 2. Right. Now, what are those? How the okay, now we'll go to the ML. ML has now it may have a value goes from -2 to +2. How those -2 to +2 will vary? This is the -2. -2, -1, 0, the +1 and +2. Right. Like you are reading this through a x-axis like that. Okay. So now specifically this electron is in now the +1 value. Right. Next, we'll look at the spin. Now that electron is pointing up. So you will say it is +half. In this case, in this question, you have to give the specific number for ML. Because the electron was a single electron was highlighted. But for a different question, like, okay, as an example, in a question, you may be asked, what are the possible uh, what are the possible ml values for an electron in 4p? What are the possible values for an electron in 4p? Right? Then you will give a range. Okay. So 4p, the principal quantum number, n equals 4, since it's in energy level 4. The L, what is L? P equals 1, right? So the L equals 1. Now we don't know which orbital is that, right? So now you should give a range. ML can have -1 to +1. So there are three different values that ML can have for an electron in 4p orbital. That is -1, 0, and +1. Okay. So three possible values. When you are not given the energy diagram like that. So normally in a multiple choice question, you will be given a question like this. What are the possible values for the ML when the electron in a certain energy level? Like that. Okay. Do you have any more questions? Are there any more questions?
No, ma'am, not for me.
Okay, right. I know we couldn't go over the uh, periodic trends, but I'm gonna post another practice worksheet like this for the periodic trends and its answer key. So please go over that and email me if you have any questions. So thank you for joining with me today. Yeah, I'm gonna stop that. Again, I'm gonna record this session and we'll post it on the Blackboard.
Thank you.
You're welcome.
Thank you.
You're welcome. Yeah.